Here, what I want to do is find formulas for the inverses of one-to-one functions, assuming that the function, the one-to-one function you're given, is actually given by a formula also. So there'll be questions like this when the time comes here. Okay, so here's our goal. Find the formula for f inverse given the formula for f of x. And f of x is assumably 1 to 1. Okay, let's take an easy example here. Okay, in each of my examples, I promise they'll be 1 to 1. And let's go ahead, and you don't have to prove that. You know, when the time comes, I'll just say it's a 1 to 1 function. Go ahead and find the inverse. Okay, suppose y equals x cubed is my function, which I'm calling f of x. X cubed is actually a 1 to 1 function. So if you would graph that, which was something I'm going to do in my next video, this would actually, the graph y equals x cubed would pass both the vertical and horizontal line tests. Okay? Now I'm going to show you guys steps here you guys want to use to find f inverse. Let me box this in red maybe. Okay? These are the steps. There's only 2 steps. One step is trivial, the other one can be trickier. Okay, the tricky part is actually the second one. Here's what you guys want to do. You want to, if you're given a formula like this, f inverse, and you've got y equals f of x, okay, assumably, if it isn't given that way, you write it like that, y equals f of x, okay, what you want to do is interchange x and y in your formula, and then solve for x, okay? Now, solving for the x is going to be the hard part. Interchanging x and y, obviously, in a formula is going to be trivial, but it's going to be necessary. Now, by the way, the only reason I'm actually doing that, interchanging the x and y, is because I want my function inverse here, f inverse, to be in terms of x, okay? My original variable. And then we'll, like I said in a future video, my next video, in fact, we'll compare the graphs of these two geometrically and see if there's a relationship. Okay, let's come down here to this one, though. Okay, so we've got y equals x cubed. That's our function. So what you want to do is the first thing is what? Interchange x and y. So I would have x equals y cubed. And then the next step, the second step, the last step really, unless maybe you want to write something explicitly at the end, you could consider that a third step. But how would you solve for y in this equation? The answer is you would take the cube root of each side. Okay? The cube root of y cubed, I should say, is y. So we've actually got y is the cube root of x. Now maybe I should have this as my third step, but really it's a matter of just writing your answer. F inverse is the cube root of x. Okay? So I start with the cubing function, right? And its inverse function is the cubing function. Okay? By the way, I will throw this in here. Okay? Maybe just on the back. Okay? So you guys get this. You remember if I compose these, I should get x. Okay? F inverse of f of x should be x, and vice versa. Let's try it. This would be what? The cube root of x cubed, my original function, is indeed x, right? Okay, on the other hand, f of f inverse of x should be x. Remember how it's the identity function? I'm not going to be doing this one with all these, just to let you know here though. I'm taking f of something, breaking into it, so I'm cubing, okay? What's the inner function is the inverse, the cube root of x. What's the cube root of x cubed? Well, it's actually x, okay? All right, so there you've got that there, and you've got that there. Seems to be working, okay? So it's just what we expected. Okay, let's go to another example. Again, this is 1 to 1. I make that statement, okay? Find G inverse, okay? What's our first step? Go ahead and interchange the x and the y, and then we're going to do what? We're going to solve for y, okay? In terms of x. Okay, probably the easiest way to do this is to multiply on each side by the y plus 1. Don't forget your parentheses. When the y plus 1 multiplies on the right-hand side, it's going to do what? It's going to cancel out with the y plus 1 down in the denominator. You don't have to slash these out. You can just do it mentally here. Those get slashed out mentally, and we're left with the y on this side. The advantage here is that we've gotten rid of fractions here, haven't we? Okay. Now, remember, I'm trying to solve for y. I use the distributive property here, okay, because I want to get at y here, and y is being protected by his parentheses here, his little buddies. We're going to break through those. So we're going to go, what, xy plus x. And now this is going to be essentially in a linear equation in y. So I have a y here and a y here, and that's what I'm trying to isolate. I'm going to get the y values on the same side. They're just first powers on these. That's what I mean by linear here. So I've got y minus xy should isolate x. And now I notice that these two terms here have a common factor being y, so I factor that out, and that's good because that's the fellow I'm looking for. It's easy to isolate now. I'm going to divide on both sides by x minus 1, and I'll make my statement this way: y equals x over 1 minus x. And then maybe my final answer, I'll say g inverse, remember g was that function, is this. Okay, so these are inverse functions of each other. Okay, that means if I was to compose them in either direction, I would end up with what? If I do it right, I will end up with just plain old x. Okay, all right, I'm not, again, I told you I wasn't going to do that composition, but you might do that as an exercise. Here's an interesting, easy little one I thought I'd throw in here. I've got h of x, and this is 1 to 1, I promise again. I should throw that in there. Okay, y equals 1 over x is 1 to 1. Okay, so what are we going to do? We're going to find the inverse. We're going to interchange the x and y. So I've got x equals 1 over y, and then 2, solve for y. Okay, the easiest way, again, is to multiply on both sides by the denominator I see. And you see I would have xy equals 1 here when the y's cancel. Okay, I'm looking for the y, so I would isolate y. So we'll just say over here, y is 1 over x, dividing on both sides by x. And I could say h inverse is 1 over x. I'd like you guys to box in your final answers showing exactly what you're asserting. Okay, what do you notice about this particular problem? H of x has an inverse which is identical to itself. Okay, this can happen. Okay, this is, we'll see the geometric conditions that this must satisfy then. I'll mention right now what this means. This has symmetry with respect to the line y equals x. Okay, we'll see that in another video though. But anyways, it's its own inverse. Interesting. Okay, let's come over here. Let's do this one. This one is 1 to 1. Okay. Notice I'm not worrying about what the domain or range are in these particular problems here. One, let's go ahead and do our interchange, x and y, 7 through, 2y minus 5. Okay. Second, solve for y. Okay. What I'm going to do is the following. I need to get at that y in there, and that's in under the radical. The function under the radical is sometimes called the radicand. I'm not responsible, but that's the idea. That's the name. Let's raise both sides to the 7th power, right? Okay. All right. You notice this is going to isolate, I'll just write x to the 7th, but this is going to isolate that radicand. Let's add 5 on both sides and divide by 2. And we'll have y isolated. So that I'll put this down. I'll go, what I call that k, so I'll say k inverse. Notice that goofy notation. It looks like reciprocal, but it's not. But this is a formula for our function, or inverse function. Okay, there it is. Okay, crash your 7s. Okay, let's do one last one. Let's mention here. I've got this function y equals p of x is x squared. Okay, let's go ahead and see if we can find the inverse here. Okay, x and y, let's interchange them. How would you solve for y? Remember, we're solving for y. Okay, you do what? You take the square root of both sides. Okay, what's the square root of y squared? Aha, fooled you. It is not y. The square root of y squared is what? Absolute value of y. Okay, this is absolute value of y. So that there's actually what? Two values corresponding to this, the plus and the minus. Okay, now if you guys think of the domain here, the only possible domain here for which this would make sense in the real numbers is for x greater than or equal to 0, because if you put a negative value for x in there, what happens? You get an imaginary value, and we're ignoring imaginary numbers in this chapter, as you may know, emphasizing graphs and things. The imaginary numbers don't appear in the xy plane, right? Anyways, do you see this? This is not a function. You know, I've got an x value popping in, and there's two values popping out. That's not a function. What went wrong? Okay, well, this turns out to be what? That thing is not one-to-one. Okay, we'll see that in the next video here when we graph this. You probably know the graph of this anyways. It's our quintessential parabola. This fails the horizontal line test, okay? Unless you restrict the domain, you know, to the positive or non-negative real numbers, which you could do, this is not going to be a one-to-one function. I'll just tell you right now, I'll do it. You guys know what the graph looks like here. It's like this. It's a, what, a parabola here. And unless you're restricting the function, you know, to one side or the other, it's going to fail the horizontal line test, okay? It's not one-to-one. Fooled you. Tried to fool you on that one. Don't forget that the square root of y squared is absolute y, all right? If y is negative and I square it, I get a positive. When I take a square root, I get a positive. Square roots have a unique value. For example, like this, see? -3 quantity squared. Don't forget your parentheses in there. That's a square root of 9, which is 3 and only 3. Notice how I got a sign change there? Okay, anyway, so keep this in mind. Pay attention to the next video also. Okay, there'll be one of these on the exam, so don't forget.